You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Securing edge and hybrid connections is essential because these pathways bridge cloud services with on-premises networks and end users. They represent both high-value conduits and high-risk exposure points. The purpose of edge and hybrid security is to ensure that traffic entering and leaving cloud environments is authenticated, encrypted, filtered, and observable, while hybrid links that tie enterprise data centers to the cloud remain resilient and trustworthy. In practice, this means treating gateways, tunnels, and interconnects not merely as transport, but as governed security boundaries. When these connections are properly secured, organizations can extend cloud capabilities to their branches, partners, and remote workers without sacrificing control. For learners, mastering edge and hybrid security means understanding the technologies and governance that keep traffic safe at the boundary, where trust assumptions are tested most sharply. Edge gateways serve as the primary control points for terminating external traffic and enforcing boundary policies. Positioned at the perimeter between public networks and cloud services, they absorb, inspect, and direct flows. Gateways handle encryption termination, route enforcement, and filtering, making them the first and last line of defense. For example, an application gateway may terminate SSL traffic, enforce HTTP policies, and forward requests only to authorized services. By consolidating these functions, gateways simplify policy enforcement and create visibility at critical ingress and egress points. Their placement and configuration determine whether edge traffic is well-regulated or porous, making them indispensable components in secure hybrid architectures. Reverse proxies extend gateway functions by controlling exposure of internal applications to the Internet. Rather than allowing direct access, reverse proxies mediate requests, providing authentication, filtering, and routing. This ensures that only validated traffic reaches backend systems. For instance, a reverse proxy may require single sign-on authentication before forwarding a request to an internal web app. They also provide abstraction, allowing internal architectures to evolve without changing external interfaces. Reverse proxies thus provide both security and flexibility, limiting attack surface while streamlining external presentation. In hybrid environments, they often serve as the controlled window through which sensitive on-prem services are selectively and securely exposed to external users. Content delivery networks distribute application content closer to users, reducing latency while embedding security into delivery. CDNs cache static content at edge nodes around the globe, reducing reliance on origin servers. Beyond performance, they also provide protections such as TLS termination, DDoS mitigation, and WAF integration. For example, a CDN may block malicious requests at the edge, shielding application servers from volumetric and application layer attacks. By blending acceleration and security, CDNs turn performance infrastructure into a protective layer. They also integrate with hybrid models, ensuring that applications remain fast and safe even when their origins span multiple clouds or on-premises data centers. Virtual private network tunnels are one of the oldest but most reliable methods of securing hybrid connections. VPNs encrypt traffic between on-premises networks and cloud virtual networks, ensuring confidentiality and integrity across untrusted links. For example, an IPsec VPN may connect a corporate data center to a cloud provider's virtual private cloud, allowing internal applications to communicate securely. While VPNs provide strong encryption, they require governance over key management, split tunneling decisions, and endpoint security. When managed well, VPNs remain indispensable for hybrid models, providing flexible, encrypted bridges that protect data as it moves between environments. Dedicated interconnects provide private, high-bandwidth links between enterprises and cloud providers. Unlike VPNs that traverse the public internet, interconnects run over private circuits, reducing latency and avoiding exposure to public threats. They are particularly valuable for sensitive flows, such as financial transactions or healthcare data. For example, a hospital system may use dedicated interconnects to move imaging data securely into cloud analytics platforms. Interconnects offer predictable performance and strong compliance assurances, though they require higher cost and coordination. They represent the premium tier of hybrid connectivity, favored where risk appetite is low and performance requirements are strict. BGP route control is fundamental for managing hybrid connectivity. By selecting preferred paths and defining failover rules, BGP ensures that traffic follows secure, predictable routes. For example, if a primary interconnect link fails, BGP can redirect flows over VPN tunnels as backup. Route filtering also prevents unauthorized announcements that could hijack or leak traffic. BGP is both powerful and dangerous. Misconfigurations can expose networks globally. As such, resilience and security at the hybrid boundary depend heavily on disciplined route governance, ensuring that traffic steering remains intentional, secure, and resilient. Network segmentation is as critical at the edge as it is inside the data center. By separating edge zones, partner zones, and core workloads, organizations limit blast radius and enforce least privilege. Explicit routing policies define which segments can talk to one another, preventing lateral movement from exposed edge services into core systems. For example, partner VPNs may terminate in a separate zone with tightly scoped routes. Segmentation ensures that edge and hybrid connections are not flat pipelines but structured, compartmentalized systems where trust is tiered and monitored. Private DNS and split horizon resolution reinforce security by ensuring that internal names and records are not exposed to public resolvers. Private DNS servers provide authoritative responses for internal zones, while public queries see only sanitized records. For example, an internal service address may resolve to private IP ranges when queried inside the network, but remain invisible externally. This prevents leakage of topology and reduces the chance of external reconnaissance. Split horizon DNS also supports hybrid architectures, resolving services appropriately depending on whether queries come from on-prem, cloud, or external users. Network address translation governs egress from private subnets, concealing internal addresses and controlling which services can reach external networks. NAT reduces exposure by preventing direct inbound connections, while also simplifying policy enforcement. For example, workloads may access the internet through NAT gateways, while outbound destinations are filtered. Concealing private ranges prevents external actors from mapping internal architectures, while outbound policies reduce the risk of unmonitored exfiltration. NAT remains a cornerstone of edge security, providing both obfuscation and policy enforcement for hybrid networks. Web application firewalls provide targeted defenses at exposed endpoints, mitigating common HTTP attacks such as SQL injection, cross-site scripting, and command injection. Deployed at gateways or CDNs, WAFs inspect requests before they reach applications. For example, a WAF may block malformed payloads that attempt to exploit vulnerabilities in back-end services. By embedding WAFs at the edge, organizations protect both legacy and modern applications from widespread attack patterns. WAFs ensure that hybrid connections exposing web services remain resilient against the most common vectors of compromise. DDoS protections absorb and deflect volumetric attacks, maintaining availability during floods of malicious traffic. Cloud providers often offer edge-based scrubbing centers, scaling defenses far beyond what individual enterprises could deploy. For example, if an attacker floods a site with millions of requests per second, DDoS protections absorb the surge before it ever reaches the application. In hybrid models, DDoS defenses must cover both cloud-facing and on-premises gateways, as attackers may target either. Protecting availability is as much about scale as it is about filtering, making DDoS mitigation an essential edge function. Mutual TLS adds assurance by authenticating both client and server during connections, ensuring that service-to-service traffic is not only encrypted but also verified. For example, an on-prem system connecting to a cloud API may present a certificate proving its identity, while the API provides its own. This prevents impersonation and man-in-the-middle attacks, strengthening trust across hybrid links. Mutual TLS represents the principle that in distributed systems, authentication must be bidirectional, with every participant proving its legitimacy continuously. Public key infrastructure governance underpins trust at the edge by managing certificates for gateways, services, and clients. PKI processes cover issuance, renewal, and revocation, ensuring that expired or compromised certificates are removed quickly. For example, a compromised vendor certificate must be revoked to prevent further access. PKI governance ensures that trust is never static but maintained actively, aligning edge identities with real-world conditions. Without strong PKI, even encrypted connections can become brittle, leaving hybrid links vulnerable to misuse. Software-defined wide-area networking introduces policy-driven overlays that optimize and secure branch-to-cloud routing. SD-WAN abstracts underlying circuits and applies centralized rules for path selection, encryption, and prioritization. For example, SD-WAN may route video conferencing over direct internet paths while steering financial transactions over encrypted interconnects. SD-WAN aligns hybrid connectivity with application context, ensuring that performance and security requirements are balanced dynamically. It represents the evolution of WAN design into a flexible, software-governed fabric that supports cloud-first architectures. Cloud Access Security Brokers extend security to SaaS consumption by providing visibility and control over sanctioned and unsanctioned applications. CASBs monitor traffic, enforce policy, and detect anomalies in user behavior. For example, a CASB may flag an employee uploading sensitive files to an unsanctioned file-sharing service. In hybrid models, CASBs bridge traditional perimeter defenses with cloud-based SaaS environments, ensuring that edge security extends beyond infrastructure into applications. They illustrate how modern edge security must cover not only traffic, but also the context of what users are doing in external services. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Zero Trust Architecture redefines how organizations secure edge and hybrid environments by rejecting implicit trust in network location. Instead of assuming that a connection from inside a VPN or interconnect is safe, ZTA applies identity-centric access controls and continuous verification. Every user, device, and service must authenticate and be authorized dynamically, with policies that evaluate context such as device posture and location. For example, an employee connecting to an internal HR app via a hybrid gateway may be required to authenticate with multi-factor tokens and a compliant device, even if already on the corporate network. By embedding ZTA principles at the edge, organizations ensure that hybrid links are not broad trust zones, but tightly governed pathways where every access is verified, reducing the risk of lateral compromise. Identity-aware proxies provide practical enforcement of zero trust by gating access to internal applications. Unlike traditional VPNs that grant broad network access, IAPs validate identity and context at the application level. Policies may restrict access to specific apps based on user role, device compliance, or risk signals. For example, a contractor may be granted access only to a project management tool, while a full-time employee receives access to financial systems. IAPs also log access events in detail, improving visibility. By shifting access control from the network perimeter to the application boundary, IAPs reduce attack surface and make hybrid architectures safer and more auditable. Egress filtering reduces the risk of data exfiltration and command and control traffic by restricting outbound destinations and protocols. Without controls, compromised workloads can communicate freely with attacker infrastructure, bypassing perimeter defenses. Egress policies enforce least privilege, allowing only necessary outbound flows. For instance, a hybrid gateway may permit application servers to reach patch repositories, but block access to arbitrary internet endpoints. Filtering also simplifies detection, as anomalous or unauthorized outbound attempts stand out clearly. By securing outbound as well as inbound traffic, egress filtering closes a critical blind spot at the edge, transforming gateways into bidirectional guardians. Payload inspection and data loss prevention add another layer of protection by analyzing traffic content as it crosses hybrid links. These controls enforce acceptable use, scanning for sensitive data such as credit card numbers or intellectual property before it leaves the environment. For example, a DLP system may block an attempt to upload a patient record to an unsanctioned SaaS application. Privacy considerations are paramount, requiring selective inspection that balances security with confidentiality. Done well, payload controls provide assurance that edge connections do not become conduits for leakage or regulatory violations, embedding governance into every flow. Remote access solutions in hybrid environments must balance security, performance, and usability. Split tunneling, where only enterprise traffic flows through the VPN or proxy while other traffic goes direct to the internet, improves performance but introduces monitoring challenges. Full tunneling, by contrast, inspects all flows but may degrade latency. Modern remote access platforms address this by integrating inspection, endpoint posture checks, and context-aware routing. For example, a remote developer may connect through a secure proxy for source code repositories, while video streaming bypasses for efficiency. Balancing these approaches ensures that remote users remain productive while edge security remains uncompromised. Partner and vendor connectivity introduces external risk that must be tightly governed. Third-party access should follow least privilege, with explicit scoping, time-bound windows, and audited sessions. For instance, a vendor maintaining a hybrid gateway appliance may receive temporary access only to management interfaces, with all actions logged. Overbroad or permanent partner access creates blind spots and liability. By enforcing structured connectivity rules, organizations ensure that hybrid links support collaboration without opening backdoors. Vendor and partner security becomes a shared responsibility, governed by contracts as well as technical controls. Telemetry design at the edge ensures that activity is visible for detection and forensic purposes. Gateways must emit flow logs, firewall decisions, certificate status, and authentication events. These logs provide the raw material for detecting anomalies, such as repeated failed connections from unusual geographies or expired certificates in use. Hybrid links must not only move traffic but also generate visibility, ensuring that investigators can reconstruct what occurred in incidents. Observability at the perimeter transforms hybrid gateways from blind pass-through devices into active, accountable participants in the security ecosystem. High availability for gateways ensures that connectivity remains reliable even when components fail. Redundant gateway instances, health checks, and automated failover mechanisms prevent single points of failure. For example, if one edge appliance fails, routing automatically shifts to a standby unit. Load balancing further distributes flows across active gateways, reducing risk of overload. In hybrid models where cloud and on-premise depend on continuous interconnection, availability is as critical as security. High availability ensures that resilience and protection coexist, supporting both business continuity and defensive assurance. Change management governs the lifecycle of edge and hybrid configurations, reducing the risk of accidental outages or insecure rules. Every rule edit, certificate update, and route announcement should follow documented approvals and staged rollouts. For example, a change to BGP routes may be tested in a sandbox before global propagation. Staging reduces blast radius, ensuring that misconfigurations do not cascade. By embedding governance into edge changes, organizations prevent their most sensitive connectivity points from becoming brittle or unpredictable. Change management aligns hybrid security with enterprise ITIL or DevSecOps practices, balancing agility with safety. Naming, tagging, and metadata standards bring order to the sprawl of edge assets. By labeling gateways, certificates, and hybrid interconnects with ownership, compliance classification, and cost center tags, organizations enable accountability. For example, metadata may show that a specific VPN gateway belongs to the finance team and supports PCI-regulated flows. Standardization also supports automation, allowing monitoring tools and audits to classify and enforce policy systematically. Naming and tagging may seem administrative, but without them, hybrid infrastructures become opaque, making security oversight inconsistent. Compliance mapping ensures that edge controls meet regulatory and contractual requirements. For example, PCI DSS requires strict segmentation of cardholder data flows, while HIPAA mandates encryption of protected health information across hybrid links. By mapping perimeter controls to these frameworks, organizations demonstrate not only technical strength but regulatory diligence. Compliance mapping also supports audits by linking firewall rules, certificates, and logs directly to control objectives. This practice integrates hybrid security into broader governance, risk, and compliance processes, ensuring that external obligations are continuously met. Disaster recovery for hybrid links ensures continuity of connectivity under adverse conditions. Alternate VPN paths, backup interconnects, and validated failover drills prepare organizations for outages in primary circuits. For example, if a private interconnect fails, traffic may reroute over IPsec tunnels until the dedicated line is restored. Capacity reserves ensure that backup links can handle redirected flows without degradation. Testing these failovers validates that theory matches reality, preventing surprises during crises. DR for hybrid links ensures that connectivity remains a resilient backbone, not a single point of collapse. Anti-patterns highlight what undermines hybrid security. Allowing any-to-any rules at the gateway erodes segmentation, creating flat networks vulnerable to lateral movement. Using unmanaged wildcard certificates introduces trust risk, as compromises are harder to detect and rotate. Exposing administrative ports such as SSH or RDP directly to the Internet creates unnecessary attack surface. These shortcuts may simplify operations in the short term but invite disaster in the long term. Recognizing and avoiding anti-patterns is critical for sustaining the integrity of edge and hybrid designs. Evidence packages for audits consolidate the proof that edge and hybrid controls are in place and effective. These may include root records, certificate inventories, firewall snapshots, and results from failover tests. For example, an auditor may request evidence that vendor access was time-bound and logged, or that redundant gateways were tested successfully. Automating evidence collection reduces burden and ensures accuracy. Evidence packages transform edge security from trust-me assertions into demonstrable assurance, reinforcing accountability at the organizational and regulatory level. For exam relevance, securing edge and hybrid connections requires identifying the right controls for least privilege, observability, and resilience. Candidates should understand the trade-offs between VPNs and dedicated interconnects, the role of gateways, and the benefits of zero trust and IAPs. They should also be able to evaluate anti-patterns, design telemetry pipelines, and link controls to compliance obligations. The exam emphasizes selecting controls that protect the boundary while maintaining usability and business continuity. In summary, edge and hybrid security is about building governed, observable, and resilient bridges between cloud and on-premises environments. Gateways enforce boundaries, reverse proxies and CDNs manage exposure, and VPNs or interconnects secure hybrid paths. Identity verification, MTLS, and PKI governance ensure trusted endpoints, while Zero Trust and CASB extend protection to users and SaaS. High availability, disaster recovery, and change governance maintain reliability under stress. By avoiding anti-patterns and generating evidence, organizations demonstrate that hybrid links are not only functional but defensible. The result is connectivity that enables flexibility without sacrificing assurance, ensuring secure and dependable operations across the edge. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.